unforeseen circumstances. All right, let's talk a little bit about methodology. We're going to talk about populations, because this morning we measured over 1,500 pennies.
No, we haven't even measured them, we just sorted them.
Okay, to be fair, you have not measured them, but you know that they exist. And at 1,500, we have a population, not a sample. Samples are small numbers, populations are big numbers. And one of the really important trends in the grown-up disciplines of chemistry is stop considering things as being samples. Start considering them as populations. Like that balloon of gas that you've got, that's not a sample of gas. That's trillions and trillions of particles of gas. That's a population. And because it's a population, there will be differences. Okay? We can start with that and then talk about methodology and then come back to it. Or we can just talk a little bit more about methodology and then talk about statistics. Let's do a little bit, let's do something up front and then come back to it. Okay? So we'll do a little bit about populations up front. Populations are larger, in fact, much larger than samples. And that's going to express itself later when we actually do a statistical analysis of our data points, that we're going to use a different statistical method because we have large numbers. There are two sets of readily available methodologies in terms of statistics. One is called the t-table and one is called z-table. I have four or five of them in my head. The z is going to be used for populations, and the t-table method of statistical analysis is going to be used for samples. Our textbook suggests that this is small numbers. Small numbers means 30-ish. There is an absolute lower limit. I think people are scared to say numbers out loud because people write those down and think that they're carved in stone. But if you don't if I have one data point, I know almost nothing about what it is that I'm measuring. When I have two, I still know very, very little, because is that linear? Is it might not be linear. It might be exponential. And in fact, if these three were the first three data points that we plotted, we'd probably go, oh, it's linear. Yeah, put your equipment away, boys. We're done. No, we didn't have enough information. Nine data points. Once you hit 9 data points, this table starts to kick in. Can't do a statistical analysis on 2 or 3 data points. It's just not enough. It's not representative of anything. You can't be we talked about precision the other day, and that precision is a value followed by an uncertainty. With 3, 4, 5 data points, there is so much more out there that you can't be certain of what's going on. So when you get to be 20, 30, 40 data points, now your materials become a little bit more trustworthy. 100 data points, 500 data points, 1,000, 1,500 data points is where we're headed. We don't. This is a simplistic answer. This one is a better one. Curiously, our lab write-up, the procedure says, do these things. All right, here's a T-table. Go put your numbers in the T-table. It's the wrong table, because we're going to have much more data for that. Okay, let's talk about populations. Populations, so this right here, they follow a statistical trend. And that trend just means they're on a trend line. They could be clustered, they could be linear, they could be exponential, they could be quadratic, they could be cubic, they're on a curve, but they're following some trend, and we can see how the population works. All right, now sometimes the values inside the population are clustered really tightly. And sometimes they're very disparate. They're incredibly spread out. All right, let's think. So I'm going to plot something measurable here. And I'm going to plot it against amount. Give me an example of something from the real world that involves a population. So we would take multiple measurements where this spread is big.
Height.
Okay. So of people?
I guess.
Okay. If we go height of people, then you include, and you're including all people. So babies too. Or are you going to limit it?
Fully grown.
20-year-olds. So you say, bam. Okay. Some people are. There are no people that have no height. But there are some people that are short. And then there are some people that are tall. And there are very few people who are exceptionally tall. And there are very few people who are exceptionally short. And there is an average. Now, if you're doing this for humans at age 20, that distribution might be bimodal, because there's women and men, and you might actually find that the whole population is made up of these and those, and so our total population has a hump in it. Okay? It's a good thing we started here, because the methodology of the question would then say, all right, if I'm going to proceed with this, I have to do one of two things. I have to deconvolute. I have to mathematically deconvolute my complex shaped curve into this curve and that curve, or exclude one of the populations. Yes. So we would go, here is the distribution of heights for 20-year-old females. And here is my average height, average. And here are my really tall people. There are my really short people. And most people fit in here. All right. Odd question. How many people are here?
No.
No. All of the population is under the curve. So when I ask, what's the probability of finding people in that range? We know that it can be done because what's the probability of finding them in this range?
100%.
Yeah, 1. The probability is 1. If you make that be a percentage, it's 100%. 100% of the population are under the curve. So the area of the curve represents the total population. We can quantify the curve a couple of different ways. The curve that I'm drawing is a curve that does not have a bias. A bias is a systematic error that leans one way. Okay. If you were in a country where you shared a land border with another country that had a very lucrative basketball system, league, and your country didn't, then maybe all the really tall people in your population have left. And now we have a skew. That would be a bias, right? The graph that I'm displaying right now has no bias. What's that shape called? It's a bell curve, or who puts its name to it? That's a Gaussian distribution. There are other distributions in chemistry. There's the most notable one that we know of for actually I'm doing it the wrong way around. For the motion of gas particles, it does that. It's biased this way. Okay. So this is a Gaussian normal distribution that we teach as being called a bell curve. All right. This is the average. We're not going to call those averages anymore. That's the mean. The mean touches the maximum curve. And then there's a couple of things that we don't know, that we haven't quantified yet, but people know about. And we just haven't quantified them. And it is how far away from the mean, either in the negative or in the positive direction, are you? This comes up in general, almost specific conversation, where things like, you're sitting in a chair. That chair was designed by somebody and it meets standards. Those standards are set by the standards committee for the furniture industry, and then also set by, I don't know if it's OSHA. I should know, because my wife chairs one of those committees about industrial standards. I don't think it's ASCII. I can't remember. And what they've done is somebody's drawn up a nice picture, and you go, well, thank you, Gareth. That's a lovely looking chair. Have you had humans sit in it yet? And humans sit in it, and they realize, well, their feet can't touch the floor. So, because you built it to the wrong scale. That when you build a chair, you want it to be usable by this many people. Okay. When you build a car, I used to have a friend. She's not that short, but she might be here, right? And her husband bought a car, bought a Pontiac Grand Prix. Tells you how long ago this was. And she says, oh, it's a lovely car. My feet can't touch the pedals.
Oh my God.
Yeah, yeah. So she would drive it by sitting in the car in an illegal fashion. But the car was not designed for this population. The car was only designed for this population, right? She was an outlier. There are lots of people involved in making things fit humans. What's the word that we use to say how far are you away from the population center, from the mean? That's called a standard deviation. And the standard deviation is something that we're going to put a number to and quantify. But in the simplest sense, without putting any numbers to it at all, you can look at a graph and go, bump, bump, bump. I understand how this breaks down. The standard deviation is called S when it's a sample, and it's called sigma when it's a population. Okay. We have 1,500 coins. Does 1,500 coins count as a population?
Yes.
It might not, because how many coins actually are there?
A lot.
When you consider that there are several million coins, pennies in circulation, and we've got $15 worth. That's what we've got. Yeah, those 1,500 coins is $15 worth of coins. That's going to be an S. The sigma, technically, is for an infinite population, which means if we count counted all of the coins, then we would have sigma. All right, at some point we're going to give up and just call this sigma. Right here, where the value gets into the weeds, right there, that's 3 sigma. The point at which you are not confident that you can tell me how far away that line is from the baseline. And this is 0. This is no deviations away from the mean. And then basically it goes bam, bam. Doing it in pen on a board, something like that. But this is -1 sigma, that is +1 sigma, this is +2 sigma, this is -2 sigma, this is -3 sigma. Do you know people who are taking a business degree? Talk to them, ask them, what does 6 sigma mean? Because in business, in real business, in 21st century business, if you are going to make something and sell it, you do not want it to fail. You are going to build your product to be out here to 6 sigma, that it is all singing, all dancing, no uncertainty, very little error, that your product will last and it won't fail over repeated uses. Okay, there's a movement in business, it's been around for about 30 years now, called 6 sigma, and it means finding all the easy things to fix and then getting every last error out. Get every last error out of your system. Okay. Where in the real world can we see a normal distribution that is narrow?
What about the acceptable, like how people's like heart rate? 'Cause I know it's supposed to be
Okay.
within a certain.
It's like a resting heart rate, so
Mhm.
it's supposed to be sort of
Yeah. Or possibly body temperature, yeah. So something like that where you have an upper and a lower limit, and you really need to be in those limits. Okay. So here, so if we were talking about measuring resting heart rates, some people who are athletes have really low resting heart rates, and some people who have congestive heart disease, high blood pressure, have high, and most people are in the middle. Does that mean that my 1 sigma is all the way here? No, it's the same. It's the same. And there's a table, and the table is in the book, and it says that this far away from the center represents this proportion of the area. Okay? So that the relationship of the sigmas, I'm calling them sigmas, not s's, just because that's the way my brain works. It's the same thing. There's my mean, there's my 1 sigma, There's my 2 sigma, there's my 3rd sigma. Okay, same kind of thing. Could you make it even narrower?
Visible frequencies.
There are things that you can really quantify. I was thinking about what can you do that was really narrow? How about numbers of fingers? Most people have 10. Some people have 11. Occasionally you'll find somebody with 12 because they have the extra digit on both hands. And then some people have less than 10. But we're going to have a really strong average that most people have 10 fingers, right? So really sharp.
Oh, yeah.
Ooh, how many fingers do they have? Yeah. Yeah, you could go by number of arms, number of legs. What's the average number of legs on the planet? It's less than 2. Because who has more than 2? But who has less than 2? Yeah. So when you average everything in, that number is less than 2. But it's close to 2. Alright, let's talk a little bit about methodology, and then we will come back to statistics again. That was just an overview of the friendly non-numeric version. We're going to only look at one set of numbers today, if we can get to it. So we know significant figures, we know how to propagate errors. Today I copied one of the appendices out of the text. You all have access to the text, but I'll share this with you anyway. And it works through, there's some word problems. If you're going to do an addition, you use this formula. If you're going to use multiplication, you use this one. And then if you've got questions that use an addition and then a division, so I'm going to measure a volume, and then I'm going to do M1V1 equals M2V2. So the measured volume uses the error propagation for one type, and then I'm going to use that volume multiplied by molarity, which has its own error, and then divided by another volume, which has its own error. And we're going to propagate those errors all the way out to the final end. Yeah. Okay, let's look at where I'm thinking. All right, let's get a couple of definitions. We've said these words, but we've not defined them. An analyte is the thing being observed. And when I say observed, why are you observing it if you're not measuring it? And then we have contaminants. All right. We all saw Tiffany's copper sulfate today. There's also a little blue bottle that's been floating around in the lab for a couple of weeks. That is a copper sulfate solution that I made that is 0.4 moles per liter. Oh, Tiffany's not here. She's taking a step out. When we made that solution, we took the copper sulfate, which was a solid, and we dissolved it in water. And it didn't all dissolve. It made a nice blue color, but it was a suspension. There was some kind of pale blue-green suspension to it, so we filtered it. And that was the copper carbonate. It's a contaminant. So now I've got copper sulfate dissolved in water. Here's a question. Is the water a contaminant? What makes something that is in the sample, part of the sample, or external to the sample? When is the thing that's in solution with you a contaminant?
When it's preventing measure, like whenever it's gonna skew your measurements.
Now, how is the thing, the contaminant, how is it going to prevent me from taking a useful measurement?
It's either gonna make something bigger, a measurement bigger or smaller than what the actual analyte is.
Yeah. Which tells us something about what it is that makes a contaminant in the first place. We're talking about, so I used the example of the copper sulfate. We made copper sulfate a bunch of times last year and then this year again. So we took the copper sulfate crystals, we dissolved them in water, but it gave us a suspension. And then we filtered that suspension, we took the copper carbonate out, and it left behind a beautiful blue, transparent solution. So the question is the water that's in the solution with the copper sulfate, is that a contaminant?
Depends on the water. Because some water, like deionized water, for example, is removed the ions, and some
Okay.
ions can cause something.
Is the water contaminant in the crystal? Or, cause don't you evaporate the water off the crystal? Or are we talking about it in the solution itself?
In the solution. Right. So it all revolves around what are we going to do with the solution? Now, while you were counting pennies in the first week of class, what were the other guys doing? Because there was another class in with you, and they were using the copper sulfate, and they were measuring something.
The concentration of.
They took the stock solution, and then they diluted it, and then they diluted it again, and then they diluted it again, and then they put it in a cuvette, and they passed light through the sample into a detector, and they plotted absorbance versus concentration. And when things were concentrated, it absorbed more light. And when things were dilute, it absorbed less light. And it turned out that the data points in between were linear. Is the water stopping you from measuring the blue color?
No.
No. Is the greenish aquamarine colored copper carbonate that we removed from the copper sulfate, would that change how much light passed through the sample? Yes. So the contaminant is something that gives a similar response to the analyte. So if we're looking at a colorimetric analysis, if you're measuring the blueness, how much blue light, it's not blue light that's being absorbed, but how much of the complementary color of blue is your sample absorbing, and you had another colored sample inside your sample itself, then yes, it would detract. But because water is colorless, it doesn't affect that measurement. Okay. If I had copper nitrate and copper sulfate both in solution, and I had assumed that it was only copper sulfate, and then I did a precipitation by turning it into hydroxides or something like that, and precipitating the copper hydroxide, then I would get a false measurement again, because I didn't just precipitate the copper sulfate, the copper in the copper sulfate, I also precipitated the copper that was in the copper nitrates. Okay.
Dr. McGuire, so like when we were doing IR, if you had something that was also IR active,
Yeah.
like the water
Yeah.
that you using.
So things that are invisible to the human eye can still be infrared active, or they can be ultraviolet active. Okay, so this is really vague. The response could be, it has a mass, there's a volume, it has a color. It's the same, response here means same type of measurement that you're using here. So for our pennies, what's the contaminant? Could be if we let a foreign penny in, or yeah, they're dirty. The grease and the dirt that is caked onto those pennies, that's a contaminant. Because the response that we're doing in our penny experiment is we're going to measure its mass. We're going to weigh them. Okay. All right. Those are analytes and contaminants. We're going to make some measurements. Those measurements need to be calibrated. That was the last thing that we did. Tiffany, after you left, we put the 25 gram and the
20 and 10.
we put the 20 gram and the 10 gram weight on the balance, and it was good to the fourth decimal. So everything is good. So calibration means setting your experiment to measure what it is that you're looking for in the way that you're expecting. Response to the procedure to known quantities. So the people who were in lab with you last week doing the other lab, they had known quantities of a blue colored solution. The quantities were concentrations. I gave them a concentration that I had measured out myself and was confident in, and then they diluted them down in ways that was systematic and that they were confident in, and then they measured their absorbance. So now I have a line. Okay, questions. How confident am I about this part of the line?
Not at all.
Maybe the trend is this. And if we zoom in, you're only looking at that part right there. Yeah. So I don't know that it's linear outside of there. How confident am I? So I've got a data point right here. How confident am I at a data point here? Yeah. Use two different words. If my measured data point is inside validated results that I am certain of, then that is interpolated. here, I don't know that that line exists. What I'm doing is I'm taking a leap of faith that it continues in the trend that already exists, and this is extrapolated. And I think it kind of gets obvious that the further this point is from this data, the less confidence you should have in it. Interpolated data can be trusted. Extrapolated data can be trusted, but you just gotta have it close. Closer is better. Okay. Let's throw a whole bunch of definitions at you. Sensitivity. How much analyte can generate a response? And this sounds like, hey, that's its own independent thing. And it really isn't. That comes back to your calibration curve, because I'm going to give you two examples. What if, let's call this response. Response on the vertical axis. What's the vertical axis called? Which one is that?
Why?
Because I want to know.
Oh my gosh.
I know, I wasn't intentional. Versus amount. Okay? Response versus amount. Response on the Y, amount on the X. Bam. Bam. What's the difference? Frame your answer in terms of that word.
The first has it was measured with a least, no,
It takes less for a response to
So?
get a response.
Give me your answer, frame your answer in terms of that word.
The first one is very sensitive.
Yes.
how is that one more sensitive? Those are long ones.
Less amount gives a bigger response.
Okay.
All right. Allied to sensitivity is the detection limit. I should probably say something more about contaminant. I can throw it here, it doesn't matter. Detection limit is the minimum amount that you can measure that you can trust. So in words, I would say that that is the smallest quantity of analyte that is noticeably different to a blank. We haven't mentioned what blanks are. Okay, is my calibration curve still up on the board? Yes, it is. Okay, so in lab, we've all done this. Beer's law. Beer's law is that the absorbance of a solution is equal to a constant that's called the molar absorptivity. It used to be called the extinction coefficient. I kind of like that a little bit better. Multiplied by its concentration, multiplied by the path length of the sample. In all of our instruments, the path length is 1 centimeter. Those cuvettes are a standard size. They're all the same. So this is not a factor. That's a constant that is constant to the material being studied. So basically, it's just absorbance is directly proportional to concentration. And I can go that at this concentration I get that absorbance, at this concentration I get that absorbance, at this concentration I get that absorbance, at this concentration I get that absorbance. There you go. There's my trend. And I can only truly trust what's interpolated. You can extrapolate a little bit, but there's something missing. The blank.
Where it's close to the X-ray number.
The blank involves this. What is the response from the instrument when there is 0 analyte? It should be 0. It should be 0, or we can set it to be 0. That it is actually an absorbance, but hey, I press the calibrate button and it makes it be 0. This is my blank. And in this particular experiment, that is distilled water. This is distilled water, and those were blue copper sulfates. Okay. Is that extrapolation or interpolation there?
The dotted line.
Yeah.
I want to say interpolation.
I think I'm just going. I think I count that. That's a real data point. 0. It's a real data point. Okay. So the blank is everything that you are going to use in your experiment except the analyte. So the analyte here contained copper 2 plus ions, sulfate ions, water. The blank is the entire sample, plus the cuvette. The blank is the cuvette and the water, but not the copper 2 and not the sulfates. So the blank contains everything in the procedure except the analyte. Technically, that is called a method blank. There are two types of blank. There's a method blank, and then there is a field blank. So that is a method blank. That everything that you did in the procedure, which you also call the method, is contained except for the analyte. A field blank is when you go out in the field and you take environmental measurements and you measure something from the same immediate environment. So if I want to know, is the preserve being contaminated by lead, right? I would go find the rusty tractor that we're worried about leaching its what chemicals into the preserve, and measure the water immediately downstream from it, and then immediately upstream from it, I would take this. This is a similar sample from the immediate environment. Okay. I'm going to do detection limits. Detection limits detection limit. When we saw that Gaussian curve previously, that went here, it's right there. It's about 3 sigma. If it's here, we can absolutely see it. It's right there when it gets into the weeds, right about 3. So our detection limit is usually about 3 standard deviations divided by the concentration that you are looking at. Okay. What else have I got? Replication, we talked about on a different day. We talked about this morning. We replicated all of the data by counting them and then counting them again. When we're going to weigh them, we're going to weigh them, and then we're going to weigh them again. Replication makes the data more precise. It takes away the random human error. When you count the coins, there's only one correct answer, but it's easy to count them wrong. So you count them, and then what we did is we counted them, and then we had somebody else bag them, and then we had somebody else replicate and validate that that was the right number. And how many times was it wrong? No. I think that maybe 4 times out of 25 bags. How many bags do we have? More than that, right?
40,
Yeah.
50.
Yeah. So maybe 10% of the time. The simple act of just counting, just simple act of counting. Can't trust it. Got to replicate it. If you do something as simple as take an object and weigh it, take it off and do it again, and then take it off and do it again, because the third one will either agree with the first one or the second one. You've got to do it until, you've got to replicate until constant value. Your values must agree. Okay, there's one last thing in terms of definitions, and that is specificity. That the method that you use has to be able to identify what you're looking at and not just everything. Okay, so say I had sodium and barium and magnesium in solution. General chemistry 1. Have sodium salts and barium salts and magnesium salts, and I wanted to specifically know the value of how much barium was in solution. I would precipitate that barium by making it big barium sulfates, knowing full well that sodium sulfate and magnesium sulfate are soluble, but barium sulfate is not. If I had copper 2+ and lead 2+ and mercury. Oh, I'm not going to talk about mercury. What else could we have? Cadmium 2+. And I added hydroxide. They would all precipitate. This would be a bad method. It's not selective. It's not specific. This method is specific. That method is not. We have other methods that a lot of the electrochemical methods. We have a sodium electrode. It detects only the conductivity for sodium. So you would use that electrode, and you'd be able to tell. Okay. Let's talk about amounts. You got that? N. What's N? That's my number of measurements. X is going to be the value of a measurement. An individual measurement. Now, we can call, I'm going to call this individual. And then I'm going to give this a subscript I. That's an individual value. X with a bar over the top is the mean. Mean is one of the forms of average, and a mean is the sum of all the values of X divided by the numbers that you measured. This is where, when individuals are reading the text, it starts to get like, oh, this is getting kind of squiggly and symbolic. The sigma means sum, which just means add the numbers together. It's kind of a threatening way of saying add the numbers together. And if there is two sets, a subscript and a superscript, it means between these limits. So add the numbers between 20 and 50 together. And then n is just the number of times that you've measured it. Then we get the standard deviation. S is our standard deviation, and we know what it looks like already on the graph. Here's what it means in terms of actual values. It is the sum of the gap between a value and the mean of the sample. This is the gap between the actual thing being the value that you're looking at minus its mean. All of that is squared. Divided by n minus 1. N minus 1 is called the degrees of freedom. Why is n minus 1 not n? Has anybody ever talked about that? This is a comparative value. And if you're comparing yourself to the rest of the world, you don't count yourself, right? It's everyone else in the world, not including yourself. And all of this gets a square root. Okay. I have one last thing. I'll do it really quick, and then when we come back, we'll do it as a calculation. Or I can just give up. Let's just give up. Want to give up? How desperate are you to go? Just in general. He's already packed up. Right, so the next thing is we'll throw some numbers at these. The first thing that we're going to do is find outliers in a thing called Dixon's Q-test. I'm going to show you the way that the book does it. It's the G-test, Grubbs test. I think the old way might be better than the new way. We'll look at both. And then after we've thrown some of our data away, we'll look at the overall picture and say, this is now a congruent set, and I can make decisions based on what I've got. Okay? See you on Tuesday. Yep. Yep.